Alright, for the first example, I want to look at this blue cylinder here. And what I'm going to do is I'm going to put it in an electric field here. You can see the electric field lines coming up like that. Right? They're coming up here. So the electric field is going from the positive charge to the negative charge. And what I'd like to do is I would like to look at this and see if this guy is going to float. Alright? So, or if this guy's floating, then what the field is, how much is the field. And these are the values of some of the things that I said about this. So it's a 1 centimeter squared end cap, right? So the end here is 1 centimeter squared. And it's 10 centimeters long, so it's a long rod. It's got a positive charge, those are what the little plus signs are. And we just want to see if it floats. And so the question is, how am I going to do that? Well, basically I've got two forces going on here, right? I'm going to have a force for the charged object in the electric field. And on top of that, that has to be counterbalanced by a force that's pulling it down. If something's going to float, if something's going to levitate, it's going to have two forces that counteract each other at most, or at minimum. Or I guess it could float with no forces acting on it, but I don't know if that's really still floating. So if I've got forces, then I'm going to have a free body diagram. Right? That's one thing I'm going to have. And the free body diagram will give me an equation for stability. And that is going to refer to the forces. And so we're going to have probably an electric force and a gravitational force. Okay, so I'm going to do those in those three ways. So I'm going to start off with the free body diagram, and that's going to show us the physics. That's going to tell us what the equation should be that we're going to use. That's going to be the main equation, but then that equation is going to have at least two forces in it. We'll have two forces in it. And so we're going to have to write the equations for each one of these guys. And then we'll have to get some numbers and stuff like that. So let's start with the free body diagram. So the free body diagram, it has some axes like this. Okay, and let's call this the x-axis. This is the z-axis. It's going to have weight. Objects have weight. And on top of that, we have a positive charge in a field that's pointing upwards. So we have a force pointing upwards. So a positive charge feels a force in the direction of the field, a negative force in the opposite direction. So since this is a positive charge, it's in the same direction as the field. Okay, so what does that mean? Now we have no net force, 0. So that means on the left-hand side we have nothing in the x direction, only in the z direction, so we only have to worry about things in that z direction. So we have the force F going up, so that's positive, and W, the weight, going down, so that's negative, and that's equal to 0. Okay? So that gets us to sort of the first part there. Now we have to work with the forces. So we need to find what the F here is. This is F, what could be F sub E. It's the electric force. And our definition for the electric force was the charge times the electric field. Now, this is what we want, right? And this guy we know, it's the 19.6 microcoulombs. And so we can just do that, 19.6 times 10 to the minus 6 coulombs times E. And then we have the weight of the object, which is its mass times the gravitational acceleration. We have 200 grams. 200 divided by 1,000 gives us 0.2 kilograms, because kilograms are the unit in the metric system. And that's times 9.81 meters per second squared. So what is that? So that's twice this, which is 19.6 times 1/10. So that's 1.96 newtons. Okay. So those are the things we're going to have to put back in here. So that force is going to go there, and that weight is going to go there. And then we can just plug them in and do some algebra. So we have 19.6 times 10 to the minus 6 coulombs, or minus 6 coulombs, is equal to 1.96 newtons. This is times that electric field that we want. So then we have to divide 19.6 times 10 to the minus 6 coulombs from both sides. That just gives E on one side, and that gives 1 times 10 to the minus, or 10 to the fifth, not minus 5, newtons per coulomb. Oh, and look, that's where we are. We have 100,000 coulombs. So that's more or less what we want, is E is equal to 100,000 newtons per coulomb. So this took some of the stuff we learned last semester. When we have a force balance problem that has to have a free body diagram, the free body diagram, if we know where all the forces are pointing, effectively gives us the main idea for the answer, which is, in this case, the electric field is counteracting the weight of the object and allowing us to levitate the bar. And then we take the forces, calculate those forces, and put them into our equation, and then just do math on the equation until we get to the end. All right. So that's more or less what that first example is giving us today. Bye now.